Okay, so now let me give you some basic ideas about the simplex method. Basically, I want to give you the intuition, the concept behind the algebra, and in particular geometry. Okay, so to really do the calculation, you need what we cover in the next two videos. But here, I hope that you can keep the something that I'm saying here in mind when you see those numbers in the next two videos. Okay, these concepts should be built into your mind, and so that for those algebra, they mean more than just numbers and the calculations. Okay, so intuitions. All we need to do is to search among basic feasible solutions, right? So we want to search among extreme points, and basic feasible solutions are great candidates for that because we can do that with computers very efficiently. And we know moving along adjacent basic feasible solutions is to moving along edges. So to moving along edges, we need to answer two questions. At a point, there are multiple edges attached to this point. Which edge should I move along? And also, once I move along an edge, when do I stop? All this must be done with algebra in general, because in general there may be 1000 variables and 2000 constraints. It's impossible to do them with graphs, right? But graphs or geometry can give us intuitions and actually some theoretical background. But here we only use graphs to give you some basic ideas. So what we need to do in algebra is to replace one basic variable by another one, right? Because we know if two basic variables and two basic feasible solutions are adjacent, then they correspond to adjacent extreme points. For example, if I want to move from one basis to another one, maybe I can choose, for example, x1 to be replaced by x5. Then I move to an adjacent basic feasible solution. So that means I need to do two things. I need to select one non-basic variable to enter the basis, for example this x5, and I need to select one basic variable to leave the basis, for example this x1. Okay, let me give you some ideas about what do these two things mean on graphs. If I want to select one non-basic variable to enter, that means I want to make it non-zero, right? Because originally it's non-basic, that means originally it is 0. So now I want to increase its value to make it become non-zero. When that happens, one constraint is going to become non-binding, and we will move along an edge, or I should say the edge, that moves away from the constraint. To see these two things, let's use this example. I have 3 constraints and 2 variables, and I have the standard form problem. I have the feasible region like this. Okay, 3 constraints translates to these 3 lines, and I have non-negativity. Suppose I look at this point x1 here. I know x1 can be calculated as 00483. Why do I know that? I choose x3, x4, and x5 as the basis, and then I solve the 3 by 3 system to get 4, 8, and 3. 0, 0 are just because they are non-basic. Okay, so now I know x1 and x2 are the candidates for entering the basis. Okay, I want to find one variable to enter and one variable to leave. x1 and x2, one of them may enter. Suppose I let x1 enters, then x1 is going to increase from 0, right? So that means originally this point x1 is attached with these 2 non-negativity constraints, right? In particular, this one is saying that your x1 must be non-negative. Your x1 must be non-negative, okay, at the right-hand side part. So moving away from x1 greater than or equal to 0 means to move along this direction, or to move along direction A, okay? Because when you want to increase x1, you must go in this direction. Or similarly, when you want to make x2 larger and make x2 enters the basis, then you need to move in direction B because you want to leave this particular constraint x2 greater than or equal to 0. Let's see another example. Suppose I move to the basis x1, x4, and x5. Okay, now x1, x4, and x5, they are non-negative. This corresponds to this point, or 2, 0 on the graph. Okay, so now x2 and x3, they are non-basic. So they are the candidate to enter the basis. Now let's see what will happen if x2 and x3 enters the basis. I mean, one of them enters. If x2 enters the basis, x2 is going to become positive. Okay? Oh, sorry, this is a typo. This should be greater than or equal to. So x2 become positive, moving away from this constraint. Okay? So it will move along direction D, similar to the previous. But here, if we let x3 enters the basis, I need to move away from this constraint. Okay, this constraint is exactly this one. Originally, I have an inequality constraint like this, but to make it equality, I need to add a slack variable x3 here. If I want to make x3 positive, that means I want to make x3 positive. That means I want to make the original left-hand side to be less than 4. Okay? This constraint is here. If I want to make x3 positive, that means I need to move along this direction. That's direction C. Okay? So the intuition behind finding an entering variable is that one variable is going to become positive, and we will leave a constraint. We will be determined for an edge to move so that we may leave that constraint. Okay? That's the idea. So suppose we have chosen one entering variable. We also need to choose a leaving variable, which will be determined when we know where do we stop. Geometrically, we stop when we cannot go any further, right? When we hit a constraint. So we move along edges so that all equality constraints will remain be satisfied. Only non-negativity constraints may be violated, right? So when do we know about hitting a constraint? The key is here. So in algebra, when we increase our non-basic entering variable, other basic variables, their values may change. And if one basic variable's value decreases to 0, this basic variable will leave the basis. And because it becomes 0, exactly it will become a non-basic variable. Okay? So you can see the entering variable changes from non-basic to basic. And the leaving variable changes from positive to 0, from basic to non-basic. So for example, if I'm here at x1, suppose I move along direction A, when do I stop? When I hit this constraint, right? Oh, so originally I'm x3, 4, and 5. I know x1 is going to enter, but I want to know which one is going to leave. Okay, I can see that I first hit this constraint 2x1 minus x2 less than or equal to 4, and that means x3 becomes 0. Okay, when I move along this direction, all the three basic variables x3, x4, and x5, their values are changing simultaneously. Okay, and at this point, x1 and x2, they are 2, 0. Okay, and if you plug in 2, 0 here, you can see that x3 becomes 0. But at the same time, you can see that x5 is still 3. And if you plug in that here, x4 is still 4. Okay, that means for the other two constraints, there is a gap between the current solution and these two constraints. Or geometrically, this constraint is binding at the point, but the other two are not. Okay? So anyway, we know we hit this constraint first because x3 becomes 0 before x4 and x5. So x3 is the one becoming non-basic. x3 will leave the basis. The new basis will become x1, x4, and x5. Why? For x1, originally we have this. x1 enters and x3 leaves. So x1 will replace x3. Okay? So the other two will remain identical. For basis BFS x2 is very similar. I'm here. Suppose I move along direction D. Now I'm asking which constraint will I hit first? This one, right? And this one corresponds to x4. I know x4 will be 0 before x5 and x3. The other x1. Okay, so originally I am x1, x4, and x5. I know x2 is going to enter the basis according to my knowledge in the previous slides. And I can see that I will hit 2x1 plus x2 less than or equal to 8 first. And when that happens, x4 will become 0, x4 will become non-basic, and leave the basis. So now x2 will replace x4. x2 replace x4, so it becomes x1, x2, and x5. So now we get ideas about entering and leaving variables. At each basic feasible solution, we want to move to another solution. In some sense, it should be better. How to get that, we're going to talk about the details later. But ideally, at a solution, I want to move a better one. The first thing is to choose which direction to go, or the entering variable. And that should be an improving direction. If I can really find that, I move along that direction, and then I determine when to stop, according to which constraint I hit first, or which variable becomes 0 first. Okay? And given this, after I complete these two steps, then I can give to another basic feasible solution. So we may then treat the new basic feasible solution as current, and then repeat. So in one sentence, the simplex method is an iterative algorithm. Okay? We will keep repeating what we're doing here, okay, for entering, leaving, until we get to a solution with no entering variable, because all the directions are not improving. So that's the stopping condition, and we call this process an iteration to move to another basic feasible solution. So in one iteration, we move to one adjacent basic feasible solution. We keep doing these iterations until we stop. So the simplex method, okay, as summarized in my previous slides, is an iterative process. And there are some properties. We only move along edges, right? We don't really go into the interior of the feasible solution. Okay, a feasible region. So suppose I have a feasible region like this. All I will do is to move along edges. As a simplex method, I will never try to examine some points that is in the interior of the feasible region, because I know that's not going to be optimal. Also, at each point, the number of directions to search for is small, okay? Because we only compare of edges. If I'm here, all I need to worry about is this direction and that direction. I probably need to decide which direction to go among these two, but I don't need to worry about this direction, this, and this. I only need to worry about the two edges. So the thing I need to consider is under control. And finally, the stopping condition is simple. I just move until I hit another constraint or reach another corner. So the simplex method is also very smart because we have this optimal condition. When I get no improving direction, that's all. I know the point is optimal and I can stop. So now we get the idea about the simplex method. In the next video, let's do how to run the algorithm in algebra. We need to really do calculations to get to the optimal solution. Eventually, you will see that's also not very hard. You just need to spend some time to be familiar with the process, with the intuition we gave to you here. Thank you.